Hi everyone, welcome back. In the previous video we implemented a superclass and two common ODE solver algorithms, that is the forward Euler method and the fourth order Runge-Kutta. And in this video we will test them out on the exponential decay problem, which is perhaps the simplest of all differential equations. All right, ordinary differential equation that governs decay is very simple. It's just the derivative of u equal minus u, and we can just write down the solution immediately, which is well, it is dependent on time, obviously, but it's simply just the exponential function with minus t in the exponent or the argument. So this is what we will solve both with the forward Euler method and the Runge-Kutta method, and we'll see how they compare, right? But before we get cracking on that, we will make a small adjustment to our ODE solver class here. We will import something called TQDM. And what this thing does is it's an implementation of a progress bar, really. So we'll see how they're doing as they're going along. And the only thing we need to do to make this work is at our main time loop, we will write TQ. We'll just wrap this thing like so. So when we call this method, when it runs through the time loop, it will show a progress bar in the terminal, which can be quite useful. So yeah, that's a neat little trick. I always do it when I want to know how long something is taking. Okay, so let's import numpy as np. From our ODE solver library, we want to import our two method, Runge-Kutta4 and forward Euler. Alright, and we also need a plotting tool. So from matplotlib import pyplot as plt. There you go. First, we need to define our differential equation. So let's just call it f to make it simple. It's a function of u and t. And what it does is just returns the negative value of u. So simple as that. And then we need to define some time points. So we'll go all the way from time equals 0 to capital T, or the end of time is 3, and we'll go 0.5 at each time step, which isn't a lot. There won't be many time steps. So our n is simply, we will cast that as an integer and round it. What we'll do is we'll write let's first also define some time points. So we'll have some time points equal linear spacing from 0 to t n plus 1, like so. And then what we are trying to contrast the two methods. So we'll do for solver class in Runge-Kutta4 and forward Euler. Yeah. So now because we'll do these both times, we'll say that our solver is the solver class in this little loop consisting of two things, and we'll input our function from here into the class, right? And then we also need to set initial conditions, which will be 1. So it will just exponentially decay down from 1. That's what's going to happen. And then we solve. U of t equals solver.solve with our time points. Then we can plot the u and the t. And we want to label these. So we'll label them as solver class dot name. Yeah, so I'm hoping that this will return a proper string with the name of the class, but we might have to implement some method. But we'll do that. We'll take that worry when it comes. we'll cross that bridge when we get to it. So yeah, that should be most of it. We'll also include the legend and then show. I think that's all we need. Yeah, as usual, I made an error by switching these two variables. So it should be t first, which will be the horizontal axis, and a u along the vertical axis, right? But it works now, as you can see. It goes very fast. And here you go. Well, it's a bit large. I hope you get the gist of it. Yeah, there you go. So yeah, I should probably include the exact solution as well, because we know that this differential equation that we defined up here has an exact solution, right? So we will also plot t, there will be a t left, yeah. Exponential function of minus t. Yes, but what we'll do is we'll define a t fine, which will be from, well, 0 to capital T, and we'll do 1001 points, and then we can plot that alongside with the other things. T and the exponential function of minus t, and we'll label it as exact. Oh, yeah, so we'll plot t fine and minus t fine. That should do. So yeah, here we go. So here we can compare all of them. So as you can see, we only have 6 points, right? That's 3, which is our endpoint, divided by 0.5. It's 6. It's very few points. And we see that the forward Euler, the less sophisticated method, is it really misses the target, right? But the fourth order Runge-Kutta is very close to the exact solution. So, and that's really good, right? And it really shows the benefit of doing more accurate methods. So I think this is a nice illustrative example of why one would devise better methods. In the previous video, we did another example with the sine function. So I guess we could do that one as well. Just go back to our test case. Yeah. So the only thing we'll do now is we'll go a bit further with the same kind of stuff, but now what we'll do is we'll return the negative sine function instead, because now we know that the cosine will be the solution of this differential equation. And again, we'll contrast the two methods. We could do more points, I think, so we'll just start with that. So now we are actually going, instead of defining the number of points we want, we are defining the number of the resolution, or the point size, right? And instead, this should be the cosine of t fine. All right. So let's try that. So the only thing we changed was our input problem, which we know the solution of, the cosine, and we'll see that works. All right, now we didn't really, the resolution was too great to actually see any difference. Yeah, so let's turn the resolution down a lot and then try again. Here, I think we need to zoom in just a tad. Let's just do this part. And as you can see, again, the Runge-Kutta, the fourth order Runge-Kutta is much closer, and you see that the forward Euler does not really do the trick. Quite interesting. And as we progress through this, yeah, it's not good. All right, so that was contrasting the forward Euler method with the vastly superior Runge-Kutta, the fourth order Runge-Kutta method. And as we saw that the forward Euler is more problematic than the Runge-Kutta method, and this problem gets much bigger when you solve more difficult equations. So that's it for now. Take care.